So my name is Kevin Brodsky. I work at ARM in the kernel team. And today I'm going to talk about a bit of security. So how to harden the kernel with protection keys. So first, very little bit of background on kernel security. So in the beginning, around 20 years ago, let's say, Linux was considered to be, secure enough. So more than Windows, which was good enough. But so people didn't really think much about kernel security, as in how secure the kernel itself was. So for instance, the entire kernel was mapped RWX, writable code, really good idea. Also, any piece of kernel code was able to write or even execute user memory. And generally speaking, it was quite easy to hijack control flow. You could smash the stack, do return-oriented programming. You have it. So yeah, since for the past 20 years or so, fortunately, we made a lot of progress. People have realized that it's a good idea to make it harder to corrupt your kernel. And in particular, there's been a lot of progress in terms of control flow integrity, so preventing control flow corruption. So in particular, we now have actual permission enforcement for kernel segments. So executable code cannot be written normally. And also it's not possible to execute user memory from the kernel directly. So PXN, that's the ARM64 or ARM name of the technology. x86 has something similar. And finally, there's been lots of technologies to improve forward and backward edge CFI control for integrity. So again on ARM, pointer authentication, branch target identification, shadow stack, and so on. Again, x86 has similar technologies. So nowadays, it's getting harder and harder to achieve arbitrary code execution in the kernel, which means that the focus is shifting to a different kind of attack, which is data-only attacks. So in that case, there's no direct control flow hijack. The code is running as it should. But there is some data corruption, which could be spatial, so out-of-bound writes, and more commonly these days it would be temporal, so something like use after free, double free, something like that. So the important thing to understand here is that basically the target object that we want to overwrite, to corrupt, is allocated somewhere, and then later, somewhere else, completely unrelated, thanks to a double free, use after free, something like that. So we have a very simplified version of a netlink send message here. So it does okay malloc, but it turns out because of some allocator corruption, what it returns is aliases with the target. And then conveniently we have a copy from user, and then we're just writing to the target object, which is not what the function intended, but because of the data corruption, that's what happens. So ultimately, the aim is typically to achieve privilege escalations, become root, ideally. And yeah, there are some obvious targets if you want to do that. So for instance, you could overwrite page tables, which could allow you to access any physical memory. So that's probably the most powerful primitive. And otherwise, since you want to become root, you could simply corrupt the struct cred in the task strut and just write 0 in the UID field and become root. We'll come back to that. So now, as I mentioned, it's in the previous slide, we have a situation where this function, netlinks and message, just overwrites some object it should never really be able to overwrite in the first place. So could we prevent that from happening? Now obvious solution is to change the page table so that this function cannot do that, but that's very expensive, that impacts all processors, so that's not really doable. Now, we'll have this thing called protection keys, which actually appeared with x86 on, I don't remember, 2017, something like that, which provides a per CPU view of memory. So what happens is that in page tables, every entry holds some key, so a few bits, and then we have some register that basically says for each key what permissions are overlaid. So it restricts permissions always. So like I said, it was first on x86. Now ARM64 also has it. I'll come back to that. And also PowerPC implements it. The key size varies between architectures. So the idea here would be to use protection keys inside the kernel to prevent data corruption. And currently, P keys are not used inside the kernel. They're only provided to user space. And specifically, we want to reduce write access using P keys. So the idea is really to focus on the very valuable targets here. It's not a systematic approach. We have to choose where to apply it. Also, it's not sandboxing. It's not compartmentalization. It's some form of loose isolation. It's really like low-hanging fruit idea. And if you're familiar with what lots of vendor kernels do, which use hypervisors to basically prevent the kernel from shooting itself in the foot, that's a little bit similar, but it's meant to be much lighter. So the scheme of that we're proposing, which we call KP keys, is to essentially have multiple levels in the kernel. So for the regular data, for almost all data, we would just use P key P0, which is read-write. And then for specific target data, which is the data we want to protect, we would make it read-only by default with a different P key. Now, let's see, yeah. The idea is that when we're at the default KP keys level, so it's like just some notion of level, it's not possible to write to the target data because this particular P key is read-only. And then we have some mechanism to switch to a different level where the PT key is writable. And then we can come back to the previous level. And levels basically, the level translates to a specific value of P key register. Another thing I should mention is that here the way we allocate keys, P keys, is static. So at compile time, we just say, I don't know, P0 is probably 0, target data is maybe 1, and if we have multiple data to product, we can have one P key per kind of data. But it's all static, just for simplicity's sake. I also wanted to mention, if you were thinking you could do that with other technologies, well, it's already the case, in fact. There's a lot of mitigations already in the kernel, like struct layer randomization, many forms of k-malloc hardening, and so on. But most of these things are really probabilistic. So they're good mitigations, but they obviously have limits. But this is not probabilistic. This is the interesting thing here. So the first use case we looked at is protecting page tables, and really that's because it's the most powerful primitive, and it's a very popular target. Because if you corrupt it, you can access any physical memory. So the idea with KP keys is that, so there's two aspects to this. The first one is we want to map page tables, so page table pages with a special P key. So with recent changes in the kernel, there's now this page table constructor, which is called for all page table pages. So conveniently, we can just add a hook here, and it will just change the P key for the page table page. Similarly, when we free the page, we restore the P key. And then what this means is that most code cannot write to page tables. And then, of course, we need to still be able to do it when we actually want to write them. So in the page table helpers, like set PT, set PMD, blah, 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 we just have something that will switch to an elevated KP keys level. So there's this bit of magic here with guard, but basically it just changes the PKey register on the way in and then back on the way back. And so the outcome is that now arbitrary code cannot write page tables. It can only be code that is meant to actually write to page tables. So this is great, but with security, the question is always, well, what does it cost? So on ARM64, like I mentioned, so P keys, KP keys are both implemented with permission overlay extension, POE. And so in terms of like what we expect in terms of overhead, there's two main ones. So the first one, probably the main one, is switching the level. So I apologize for a bit of assembly here, ARM64 assembly. It doesn't really matter what the details are, but mainly we're writing to some system register, POR EL1. That's the PKey register, basically. And then we have an ISB, which is a barrier, which is very expensive because it will flush the pipeline. That's just a requirement when writing to this kind of system register. The other overhead is that when we want to change page table pages, change their P key, we have to modify the linear mapping. So we have to modify the page table mapping, the page table pages, in fact. And we have some interface for that, set memory P key. So that's changing some bits in the PTs. And then we'll probably have some more overhead because the hardware will do checking on every memory access. It's expected to be low in comparison. So the problem is there's currently no hardware implementing PoE on ARM64. So, oh, and by the way, I should have mentioned, KP keys is a generic framework. It's not specific to ARM64. Any architecture implementing P keys should be able to use that, but this proof of concept is on ARM64, so that's why the benchmarking is also on ARM64. So we put together some mock implementation for benchmarking, and what we do is instead of using this POR EL1 register, which we don't have on current hardware, we just use another register. And the rest is basically unchanged. We still have a barrier. We still set the P key, which does nothing, but it's the same cost basically. Should be very similar cost. And so we've chosen some benchmarks to run, and that are page table heavy, that do a lot of page table changes. One is classic Kernel bench, which just builds a kernel, but that means forking a lot. And then we have some micro benchmarks, like calling fork map in a loop, written by David Hildenbrand originally. And then test vmalloc has some vmalloc micro benchmarks. So fork map is like user page tables. Test vmalloc is kernel page tables. It's the same idea. Now, yeah, when we've done this benchmarking, realize that the overhead is actually really high, especially on micro benchmarks. And think a bit about this, then we realized, well, it's actually very common to write many PTs at once. So when you do an mprotect on, I don't know, on 1,000 pages, you will go into this loop, right, calling set PT. Obviously, this is extremely simplified. You will call set PT 1,000 times. And because of the way KP keys work, you will have basically 2 ISBs for every page. That's really bad. Now, fortunately, there's these hooks in most places that modify PTs in a loop like that. So there's this lazy MMU mode. And that's very convenient because what we can do is say, okay, so if we enter a lazy MMU mode, we switch KP keys level to the one that allows us to write to page tables. Then set PT and so on just will do nothing about KP keys level, and then when we leave the mode, then we restore the level. And this was recently improved by a colleague of mine, Ryan Roberts, so it's working better, and it's now used on ARM64 upstream as well. So having said that, the results, so these are like percents are slowdown versus the baseline, which is 615. Oh, sorry, I'm looking at that. So this is percent of slowdown versus the baseline 615 RC1. This is run on Graviton 3, so very modern ARM64 hardware, 64 cores. So first, looking at current bench, which is like some real workload, let's say, we can see that the overhead are actually quite small. And looking at system time, we can see that batching basically halves the overhead, so 1.6 to 0.6%. Now the micro benchmarks are where we see the huge difference. So forking basically, well, used to be 3 times as slow, now has almost no overhead. And for mnmap and vmalloc, what we see, especially on vmalloc, is that without batching, basically the overhead increases with the number of pages that we're allocating, because it's proportional to the number of PTs, basically. But with batching, we do it only once for the whole set of PTs. So the overhead actually proportionally decreases with the number of pages. It's still not negligible, the overhead with batching in some cases, especially with a few pages. But remember, these are micro benchmarks, so in reality, it may well be quite acceptable. And again, I want to mention, this is really lower bound estimate, because we won't have a real implementation, but it should be quite close. And I should have mentioned, orange means statistically significant. So this, for instance, is not significant, so it actually might be basically the same as without protection. All right, so that was about page tables. Any question on this? All right. Yeah.
What happens if you succeed to do trying to do the write operation on a memory that is
Yes. All right. So in that case, if you're trying to write to page tables outside, you will get basically a page fault. And that will crash the kernel, basically. You could imagine a policy where instead of crashing the kernel, you will just log it, report it. This would be possible as well. Yeah. But generally speaking, the issue is that recovering from that is very difficult. What do you do once your kernel is corrupted? Yeah. Thank you. So now the other use case we've looked at is protecting struct cred. So again, struct cred, corrupting it leads to very straightforward privilege escalation, becoming root. So there's already some special handling in place because it's, again, really obvious target. So you're not supposed to directly write to the active credentials. What you're supposed to do is call prepare creds, get new credentials, do whatever you want on them, send them to whatever you want, then commit creds will basically atomically change the active cred to the new creds. So this is great, but actually nothing stops you from corrupting credentials. So the idea is to enforce that model. So with KP keys, the way we do this, there's kind of 2 cases. The first one, the most common one, it just works. Basically, you call prepare creds, you get some read-write credentials, you do what you have to do on them, you set them to what you want to do, to what you want. Then when you do commit creds, basically this object is moved to protected memory, which has a different P key, so same idea as for page tables, but we use another P key. Now, there's also override creds, and in that case, the programming model is different, so we can't do this. So you still call prepare creds, you get a read-write struct cred, and then you have to call protect cred, so a new function that will move it to read-only memory, and then override creds. You would call that on that protected struct. So that's a proposal. You have that requires changing quite a few drivers, but it's not all over the kernel either. Most kernel code never touches credentials. So just a few details. So credentials are allocated using KMM cache. So the way it works is that we have a new flag, slab set p key, to allocate memory with a given p key. And like for page tables, some KMM cache and some credential helpers need to switch KP keys level. So we insert some guard that will switch KP keys level as needed. So in terms of known problems already with this, one is that RCU needs to write to credentials. Because typically credentials are freed using RCU. The problem is that RCU doesn't know if an object is protected or not. So right now, RCU will just always switch KP keys level. So that's likely to be slow. Haven't actually measured it yet. There's solutions for that, probably. We can maybe tweak RCU so that there's some flag in the pointer. But yeah, haven't thought too much about it yet. Another one is that, so I said that, no, sorry. I said that current cred isn't, enforce that current cred isn't writable. I mean the object, the credential objects. The pointer in the current task struct is still writable. That is much harder to fix with KP keys because it's just one field in the task struct, and the whole task struct has to remain writable. So there are some ideas to improve, well, to work with that, but it's a lot less straightforward. Right, so what's the state of this? So for the first part, which is the whole KP keys framework, the ARM64 implementation, and the page table protection, so there's an RFC on the list, which is already at v4. And for the struct cred hardening, there's a separate RFC, which includes everything that I've mentioned so far. Yeah, so like I said, currently this is only implemented on ARM64, but there should be no major difficulty with implementing it on x86 or Power. The second RFC is completely generic. The first one, yeah, has the ARM64 implementation. So I've talked about using KP keys for making data mostly read-only. That's one way to think about it. It's read-only except in some small window of time. Now you could do also other things with protection keys. So you could use it to make data to ensure the confidentiality of secret data. So for instance, on ARM64 we have a case where we have pointer authentication keys, and if user space is able to read them, or like an attacker is able to read them, it could defeat pointer authentication in user space. So ideally these should not be readable most of the time, and that's one thing that we could use KP keys for. Another thing that we could use it for is to do some better sandboxing on JITed programs, so eBPF programs in the kernel. And for instance, we could prevent eBPF programs from directly calling kernel functions. Now, this is something that the eBPF verifier already does, but the idea here is to strengthen that isolation. And to finish, just a few interesting resources. So there was a series in 2021 from Intel that did something very similar, protecting page tables using P keys. It was specific to x86. This series didn't go anywhere. I think there's a few reasons. One of them was apparently the cost of modifying the linear mapping, of setting P keys in a linear mapping. It shouldn't be less of a problem on ARM64, but yeah, I mean, the results don't show this on ARM64 at least. So this is quite encouraging. And again, so the KP keys is generic, and that's really a big difference in approach. I mentioned before that the batching is based on this lazy MMU that's now leveraged on ARM64 using Ryan series. That's merged in mainline. Finally, if you're curious about the first couple of slides, I can really recommend this talk from B-Sides, Canberra, about the history of Linux kernel hardening. It's very entertaining and very, very frightful at the beginning, especially. On that note, that's me. Is there any question?
Do you have any figures on how many historical exploits would have been prevented with each of these two mitigations you're talking about?
No, I don't. This is a good question. We could probably count CVEs, yeah. Yeah. What I did do is look at classic attacks on page tables and on like published papers, basically, and most of them would be mitigated. Not all of them, because some are very, very smart. There's one case where a page table page is overlaid on another page table page, and the thing is, because we have one P key for all the page table pages, if you are smart enough to overlay one on top of each other, you will defeat that protection. But I think this is a small minority of the attacks, yeah.
But also just having these figures might be good to sort of inform people about whether it's worth the overhead to turn on
I agree.
Or just merge the patches in general.
Yeah, that's actually something I would be interested to get more information about, if we can, how we could count CVEs on that. But yeah.
I think that's basically a database of all kernel CVs now, right?
Yeah.
That you can sort of.
But can we just use keywords to search it and say?
No idea.
We could, yeah. But yeah, interesting. Thank you.
So if the keyword is just use after free,
yeah, but this is a bit more specific here, I guess. Yeah.
But,
yeah.
Yeah, it's more of a comment because I will be talking about CVs in the kernel tomorrow, and there is the information, all the files that are affected for each CV, that like 6,000 CVs that now are in the kernel.
Yeah.
And also you have the description, so you can easily, and it's JSON, so it's easy to parse and search for keywords.
Yeah, I think this is definitely a good idea. It would be an estimation because, as I mentioned, it's hard to be 100% sure if we would mitigate a CVE just from keywords in the description. But yeah, I think this is a really good idea. Yeah, thank you.
More questions? I'm going to heat your coffee.
Thank you. You mentioned it about pointer to be writable. As far as I understood, this PKE's technology is granularity is page table, right?
Yeah.
So basically, as far as I understood, to fix that problem with pointer, you need to move to granularity to cache line, correct?
Yeah. So this is the main limitation, I would say, of anything that's PKeys based, is that the protection happens at the page table level, so it's a page table entry, the granularity, basically. I mentioned probabilistic mitigations. Well, one of them is memory tagging, and memory tagging is at the on ARM is at the 16-byte granularity, but maybe it could be used for that purpose, but it's not exactly the same deployment model, and it's also not the same overhead. So, yeah, I think there's a lot of. I think this is a problem, in fact, with all those. We have lots of tools now, both in software and in hardware, to mitigate memory corruption, and the difficult thing is to use them together in a way that makes sense. And it's also, it can be hard to compose. So for instance, memory tagging is typically used it's typically used to protect memory allocations, to have different tag for each allocation. Now, if you want to use it for other things, like having sub-parts in a struct, could be doable, but you don't have 1,000 bits, you have 4 bits maybe. So you have difficult choices to make. Yeah.
So, any more questions? Or is it time for photo?
Probably.
I think it is. So,
all right, thank you.